Greetings, physicists. This is a video, again another algebra video, and specifically we're going to be focusing on objects in free fall. This video will be very similar to the video on how to solve constant acceleration problems because for the most part we're going to assume that objects that are in free fall have a constant acceleration. Well, what makes it different is that value of that constant acceleration near the Earth's surface is always the same number. So let's take a look at some problems. This will be relatively short. We have a heavy rock falling from rest. It's going to be dropped off a cliff. It's going to fall 100 meters, hit the ground, and we have two questions, which is how much time does it take and how fast will it be moving when it hits. So we're going to go through and find some givens right away. I see from rest, lovely keyword, glad they included it. That's a V0, and that's a V0 of 0. From the top of a cliff, falls 100 meters before hitting the ground. That is a delta x, that 100 meters. Right there. It falls 100 meters. It doesn't start at 100 or end at 100, so it's not an initial or a final. It is a delta. And it says, how long does it take the rock to fall to the ground? And what is its velocity when it hits? Now there's a missing given here, as there will always be in almost any free fall problem, which is that because the rock is falling, free falling, we can say that its acceleration is 9.8 meters per second squared. Now there's another issue to complication to free fall problems, which is direction. So it always helps to draw these. I have not put any directions in yet. So I have these three givens. Let's draw this. We have a cliff, we have a rock, and it's going to drop from rest, and it's going to go this way. And the two things that I care about right now that have direction, I mean the V0 technically has direction, but it's 0, so it doesn't really. The two things that I care about are the delta x, which is this, there's my delta x, and the acceleration. And if I draw arrows, actually, the delta x is from here to here, so that's the vector of the displacement. And if I draw, and I drew one for the acceleration is downward. Those are both in the same direction. For my purposes, I can either choose up to be the positive direction or down to be the positive direction. And I'm going to choose down to be positive. Not everybody agrees with this. There are some people out there who will tell you, always make down the negative direction. Notice if I do that, then my acceleration would be negative and so would my displacement. And when they divide out at the end, the negatives will cancel. And that will certainly work. But if I make them both positive, it also still works in this case. But you really want in free fall problems, if there's a complication to them, it's make sure you know what direction everything is going. Some stuff could be going up while other stuff goes down. You need to pick one direction to be positive or negative. So I'm making my choice now. I'm going to say that downward is the positive direction, which means I'm going to leave x, the delta x, as a 100 meters in the positive direction, and I'm going to leave acceleration as a 9.8 meters per second squared in the positive direction. So I have my givens. I have the V0, the delta x, and the a. I am now looking for my unknowns, and here they have two. How long does it take? So that's a delta time. And what is the velocity when it hits? So that is a v final. Like so. Now I just go through my list of equations. And for my list, with these givens, it looks like to get time, but I have V0, x, and a. I might actually be able to do both of these with the same equation. Let's see. No, I can't. Okay. So I will do for time, I will do this one. I will do delta x equals V0 delta t plus half a delta t squared. And for v final, I will use this one. I will use v final squared equals v initial squared plus 2a delta x. Those will work for my two unknowns here. So I have them, and now I need to solve for my various unknowns here. Now, I could, for the first one, this is a quadratic equation, so if I'm solving for time, I can do the quadratic formula, but there's a simplification, which is that 0. So that's actually going to take away one portion of the quadratic, so I don't really need to do a lot of work there, or as much as I might need to. So if I do this, if I rearrange for delta t, I should get 2 delta x divided by a, and then I have to square root that, and that should be my delta time. V naught being 0 also simplifies this equation, so when I solve this equation, let's do that real quick, I should get v equal to the square root of 2a delta x. Good. So I need a and I need delta x. Well, they gave us easy numbers, so delta t. If I do the square root of 2 delta x over a, square root of 2 delta x was 100 meters. Gave us an easy number. A was 9.8 meters per seconds squared. Well, that's not too bad. 200 over 9.8 is going to be under the square root. I'll just do that real quick. And I'm getting 20.4. So under the square root, I'm going to have the square root of 20.4. And if I look at my units, I'm going to get meters canceling. 1 over seconds squared is the same as seconds squared. So I'm going to take the square root, and I'm going to get 4.5. So I get 4.5. The square root of seconds squared is just seconds. And I was looking for a time, so that works. So it takes the rock about 4.5 seconds to fall those 100 meters. Now let's look at how fast it's going. Square root of 2ax, so the square root of 2, acceleration is 9.8, x is 100. So let's do that. Square root of 2 times 9.8 times 100. And I get 44.27, but I'm going to round it to 44. So 44. Oh, I didn't put units in. Under the square root, the 2 has no units. The 9.8 is meters per second squared. The 100 is meters. So I'm going to have 2 meters on top, meters squared on top over seconds squared. If I square root that, I just get meters on top and seconds on bottom. Good. I wanted a velocity. So the rock falls for about 4.5 seconds, and when it hits at a speed of 44 meters per second. I often see novice physicists make an incorrect assumption here, which is that the final speed of the rock is 0 because it's hitting the ground. Now, the error there is talking about the time interval. Yes, the rock will hit the ground and come to rest, but it is not at rest at the end of the fall. So if maybe I can draw this, let's see. I'm not known for being able to draw great pictures, but we'll try. So if the rock is here, it's going to go downward, it's getting faster, and then right before it hits, if I draw this just before it hits the ground, it has its final speed. And that speed is 44 meters per second. And then it hits the ground, and now we have an entirely new time interval because it does take some time to impact the ground. We will get into this in the collisions chapter. So don't make that error in assuming that the final speed of an object that hits the ground when it falls is 0. It's not. They're talking about the final speed, the exact instant, right before the impact. And then the impact is a completely different interval. So keep that in mind. All right, let's go on to the next one. Okay, springbok antelope. This is a fun one. I used to go to a bar called Springbok. Springbok antelope extends its legs forcefully from a crouch and jumps. This is basically the antelope jumping. There's the acceleration period while it's rising from the crouch, and then it leaves the ground and it goes up in the air. And if you ever see videos of these, this is really an amazing feat. And if you haven't seen a video, we're gonna calculate and you'll see why. It's so amazing. So what we have here, two questions. What speed does the springbok have as it's leaving the ground? And then how high up does it go? I like this kind of problem because there's a lot of givens that are not explicitly given. So let's go with, I'm going to do a drawing actually. I'm going to do a beautiful antelope drawing. Okay, there's my antelope crouched. Then he stands up. And then, and so the ground is here. So that's there, and then he jumps up into the air. Beautiful. There are two intervals going on. Okay, they ask what speed does it leave the ground? Well, that's at this point. And then they ask how high does it go? And that's at this point. So that's two completely different intervals. So we have this interval here, and we have this interval of time here. Keep that in mind. So we could label them. We could say this is point A, or yeah, point B and point C. So now I'm going to label a couple of things. I'm going to assume at point A, that's a starting point. And so my assumption there is that the velocity at point A is equal to 0 meters per second. Because it's crouched down first. It's preparing to move, but it hasn't moved yet. We have, during this interval from A to B, the acceleration. We can call it acceleration AB. That's constant, and it's given to us. It accelerates at 35 meters per second from A to B. So let's call that a 35 meters per second squared. So we also have the we have the distance that it rises up. So it starts in the crouch, and its center of mass is maybe here somewhere, and then it rises up from the crouch, and its legs have extended, and they've extended by almost an entire meter. That distance there is a delta x, and we'll say it's the delta x from A to B, which is and it's the vertical change in its position from A to B, or over the AB interval, is 0.70 meters. And that's what we know about the beginning. Well, then it leaves the ground, and from B to C, we have it going through the air. So now it's going to go upwards, and it's going to go upward at some initial velocity until it gets up to C, and it can't go up anymore. And when it can't go up anymore, its velocity in the vertical direction will be 0. So the velocity at point C is 0 meters per second, which is the same as velocity at point A. Interestingly enough. We don't know how high it goes. In fact, that's one of the questions. We do know, though, that the acceleration during that point, as soon as it leaves the ground, it's in free fall. Now, it may be going up, but because gravity is the only thing acting on it, we'll say that the acceleration from B to C, that is 9.8 meters per second squared. And I think that's all the givens I can get out of this. Now, we need to be very careful about these givens. If I write them all down like this and leave them, I'm going to get this problem wrong because I haven't accounted for direction. And there are definitely some different directions going on. Again, we can make up positive or we can make down positive, and either way will work. I think intuitively we want to make up the positive direction because this thing is leaping, it's starting at the ground. That seems to be an easy assumption to make. I want to show you that it works either way. So I am going to make downwards the positive direction, and I'm going to make upwards the negative direction for this problem to show you that it does work either way. So let's look at our givens. VA. Well, VA is 0, so that doesn't matter. That's not, direction doesn't come into a 0. The acceleration from A to B is 35 meters per second squared. Well, it's accelerating from here to here, and that's moving upward, and I define my up as a negative direction, so I'm going to make that a negative acceleration. It accelerates up in the negative direction. The delta x from A to B, that's this business here, that delta x is also in the up direction. It's a displacement that goes vertically. vertically straight up. So I'm going to make that a negative 0.70 meters. The velocity at c is 0. Again, we don't care about zeros, no direction there. The free fall acceleration is gravity, and gravity always pulls toward the center of the Earth, which in this case is down. So I'm going to say that's a positive direction, so I'm going to leave, I'm going to leave the acceleration from b to c as a positive number. Now everything matches direction-wise, and I shouldn't get into trouble with that. So 2 questions: leave the ground at what speed, and then how high does it go? So my unknowns then, if I'm writing them out, with what speed does it leave the ground? That's the speed at point B, because that's where it leaves the ground. So my question mark is the velocity at point B. How high does it go? That's the distance at point C, or the delta x from B to C. It leaves the ground at point B, it travels to point C. The difference in those distances should be equal to how high it goes. And so we'll say that that delta x, well, actually technically we have to include the distance from point B to the ground. So I don't think it's possible to get that unless we assume that when it crouched, its center of mass was actually on the ground, which is not reasonable. I would guess its center of mass is somewhere up here. So I don't think we can get the absolute distance from point C to the ground. So I'm just going to say that the only thing we really can reasonably be expected to calculate here is the distance from point B to point C. So I'll make that my question mark. Okay, let's see what equations we're going to need. So I have givens and I have unknowns so far. To get VB, VB is the last point of the first interval. So it's like a final velocity. And I have the initial velocity, and I have the acceleration, and I have the distance. So it looks like I'm going to do a VB squared equal to VA squared plus 2A delta x. The A here is the AB, and the x here is the AB interval. Good. That will get me, and I know all of those things other than VB, so I should be good. To get the distance for the BC interval, I have the velocity at C and I have the acceleration from B to C. I need another given. 2 givens is not enough. Well, look. If I solve my first equation, I will have VB, and VB is the first point of the second interval. So VB is every B point here is an interesting point because it corresponds with 2 separate intervals. So I'm actually going to need to solve the first equation so that I have a given for my second equation. This VB will become a given later. I love these kinds of problems, and they do show up on tests, so be ready for that. So, and I think I'll use the same equation. The v final squared equal v initial squared plus 2ax will work for the second equation as well as the first. Well, let's go ahead and solve that first equation. I am looking for VB, so I know VA is 0, so that's not going to be a factor here. So my VB will just be the square root of 2a delta x, and this is, of course, the AB interval. So when I plug this all in, square root of 2, the A was given to me, and I made it negative, so that's 2 times negative 35 meters per second squared times my delta x for this interval was negative 0.70 meters. And let's multiply that all together. 2 times 35 is 70 times 0.7. All right, 70 times 0.7 divided by, nope, that's correct. 49, of course, and the square root of 49 is 7. So that comes out to a nice even number, or round number, 7. And the negatives cancel when I multiply those together. Good, because otherwise this would be a nasty square root. I have meters times meters on top, which is meters squared. I have seconds squared on bottom. When I square root them, I will just get meters over seconds. And because these numbers both have 2 sig figs, I should have a 2 sig fig answer. So this is technically 7.0 meters per second. That's how precise I can be. All right, that's my VB. And now that I have it, I should be able to use it to answer the second question, which is how high does it go? And that's in the BC interval. So let's do the BC interval. We're going to use the same equation because we have VC. We can do VC squared, which is the final velocity for that interval, equal to VB squared, which is the initial velocity for that interval, plus 2A, and this is the A for the BC interval, and the delta x for the BC interval. Well, now we're looking for delta x. We're not looking for the velocity this time. So I'm going to have to rearrange this equation a little better. I'm going to do VC squared minus VB squared divided by, no, scroll up, there we go, divided by 2A, that's the BCA, equal to the delta x for that interval. And now we can plug things in. Our VC squared was just 0, so that's nothing. We just calculated our VB, and that's 7, which was a, hold on, I got to make sure this is correct. I have to make a change here, I think. We said, we have a square root, right? We had a square root before. And when you take a square root, you can get a plus or minus. So the technical answer here is plus or minus 7 meters per second. Either of those seems to be valid. But we know, if we go back up here, that VB is in the up direction. So the answer we need to choose is the negative one. That's definitely going to be a -7. It would be positive on the way back down because when the springbuck falls back to the same height, we know it's going to have the same speed that it launched with. So that the reason we're getting a plus or minus is because this thing follows a parabolic curve and it will actually hit 7 meters per second speed at 2 different points. But at one point it'll be up and one point it'll be down. At the point we're looking at, which is point B, it should be negative. And I have managed to drag everything on top of everything else. There we go. So get rid of that there. So when I plug in here, this is a 0 that I'm starting with, subtracting, and underneath this, it's not going to make a difference here because I'm actually squaring it, but just for the sake of continuity, that's a -7 meters per second, which I'm going to be squaring. Okay, and so I'll keep going here. On bottom I have 2, and the A is 9.8. And this is a downward acceleration, so it is positive. So that's a meters per second squared equal to a delta x. And that's what we're looking for. So when I square -7, I get 49. Give myself some room here. When I square -7, I should get 49, so it'll be 0 minus 49, so I'll get -49 on top. When I square meters per second, I get meters squared over seconds squared. On bottom, 2 times 9.8 is 19.6, and it's just meters per second squared. When I divide those, 49 divided by 19.6, I should get 2.5 meters, but negative 2.5 meters. You think, would it jump negative 2.5 meters? How is that possible? But remember, at the beginning of the problem, we said that the up direction is the negative direction. So it did jump 2.5 meters in the up direction. So you just have to be able to make that, that connection there. If we had made up the positive direction, I guarantee you when we did our math, it would have come out as positive 2.5 meters. So either way you do this, you will get the correct answer, which is 2.5 meters in the up direction. That's pretty high up. If you're looking at a standard classroom, the ceiling is usually 2.5, so, or 2.5 to 2.8. So this springbok is actually capable of leaping over a one-story building, or at least over the ceiling of a one-story building. So it's a pretty good vertical. He'd be a good basketball player. All right. Let's do one more. A volcano ejects a chunk of rock straight up at a velocity of 30 meters per second. Ignoring air resistance, what will be the velocity of the rock when it falls back into the volcano's crater? And there are actually some answer choices here. So we have answer choice A. Will it be less than 30 meters per second? Answer choice B. Will it be 30 meters per second? Answer choice C. Is it 0? Answer choice D. Is it negative 30 meters per second? And answer choice E. Is it greater than negative 30 meters per second? So let's look at these, see what makes sense. And it actually would probably help to draw this, I think. So we've got a volcano. There's the crater. The rock is probably coming from somewhere down in here where the lava is, and then it shoots straight up, and it goes to some height above there, which, nope, doesn't tell us height. But it tells us at the beginning it's going at 30. So this problem has actually chosen the positive direction for you. If it says the rock had a positive 30 meters per second velocity, it's saying up is the positive direction, because we know it's going to be going up. It says so. And then it goes up here to the top, and then it falls all the way back down, and it's going to get at the same spot right before it hits the lava again, and it says how fast is it going when it gets back down there. So right away we can eliminate some answer choices. When it gets back to the bottom, it will be going downward, so it should have a negative velocity. Now if this thing said speed, hang on, if it said what will be the speed of the rock when it falls back into the crater, speed is not ever negative. It can't have a direction. Speed is just magnitude. And that would change what we're going to say here. But because it says velocity, and because we know the rock should be going down when it gets back there, we can eliminate any positive answer choices. So I'm going to take A and B off of our possible answer choices. Now it's about to hit. Again, don't make that mistake of thinking that because it hits, it's going to go to 0. It will go to 0 after the hit, but that's not the interval that we are considering. We are considering right as it's about to hit. So we cannot make 0 an answer choice. So what we're really looking at is either minus 30 or less than minus 30. Sorry, I think I said greater than originally. Well, what could cause it to do that? I think we have one more one more set of words that are going to influence our choice here, and the ones that make sense to me are these. We are ignoring air resistance. Air resistance is not going to slow this object down during its trajectory. If it slowed down, we know that without air resistance, when it goes up, it should accelerate. It's going to lose speed all the way to the top, and it's going to have the same amount of acceleration all the way back because of the distance it travels. So this thing should hit with the same speed that it started with, except if there was air resistance. But there's not. So I have to get rid of this answer choice. Oh, come on. There. Yeah, I have to get rid of that answer choice. It can't be less than negative 30. Or different than negative 30 in any case, because there is no air resistance. If there was air resistance, I think E would be the appropriate choice. But there is not, so we're going to have to go with D. All right, this is pretty standard set of free fall problems in one dimension. They don't get a ton more complicated than that. Hopefully this was helpful.